Hi, my name is Ching and welcome back to Data Structures in C++. In the previous lectures, we have learned the basics of C++ and complexity analysis using the big O notation. Now it is the right time to start exploring data structures. In this lecture, we're going to talk about some of the easiest data structures, stacks, and queues. Then I will show you how to translate ideas into C++ code. This is called the implementation. During that, I will also show you how to extend the existing C++ code using templates. Templates are an efficient way to reuse C++ code. Let's start by talking about what stacks are. Stacks are ADTs, or abstract data types. Or in other words, stacks are collections of data. But the data type can be anything, such as primitive types, built-in classes, or custom classes. If the word stack sounds familiar to you, that's because we already mentioned that in the C++ memory management lecture. The stack memory is how the system manages automatic variables and function parameters. In the stack memory, you always push new variables on the top of the stack, and always pop from the top of the stack. That's exactly what stacks do. However, stacks are basic data structures. They have far more applications than just for memory management. You can imagine the stack data structure as a stack of plates, as shown on the right side. You can only add or remove the plate on the top. So those are the two main functions of stacks, push and pop. But sometimes we have additional functions to make it easier to use stacks, such as the top function, which returns the element on the top of the stack but doesn't remove it from the stack, and the size function, which returns the number of elements in the stack. Alternatively, stacks are also called LIFO because the rule is last in, first out. Let's use an example to demonstrate how stacks work. First, we use the top function to get the element at the top of the stack. In this example, top returns the element 2. Then we push the number 1 to the top of the stack. If we call the top function again, we will get the element 1. Next, we use the pop function to remove the element from the top of the stack. If we call the top function again now, it will return the element 2, since 2 is now sitting at the top of the stack. This idea seems to be very straightforward. All we need to do is track the top position or index inside an array, and we can implement a stack easily. Let's take a closer look. Now let's try to translate our idea into code. More specifically, we'll define the stack class with member variables and functions. To visualize the stack class, we use an array of size 5 to manage the elements. In this example, each element is an integer. Each position in the array is represented by its index, from 0 to 4. Everything else is the same as the last slide. Here's the C++ code to define the stack class. Let's look at the private variables. The first variable, size, defines the capacity of the array, or the maximum number of elements the array can hold. In this specific example, we use the keyword static const here to prevent any accidental modification of this variable. Then we create an integer array of size 5. We don't need to initialize this. We use another variable, count, to keep track of the number of elements in this array. This count will be updated every time when the array is updated. At the very beginning, there's nothing in this array, so the count is equal to 0. Then the following are the public functions. By making them public, any stack object can call those functions directly. The first is the push function. It pushes an integer item to the top of a stack and doesn't need to return anything. The pop function doesn't need any parameters, but it will remove and return the element from the top of the stack. The size function returns the number of elements in the stack. The top function returns the element from the top of the stack without removing it. Please note that the stack class can only handle integer data types, as highlighted in red. Now we got a problem here. What if we want a stack for another data type? Do we have to make a separate stack class for each data type? To solve this problem, let's introduce the C++ template. Previously, our stack class only contained integers. What if we don't want to specify the exact type? What if we could just use a placeholder to represent any data type? C++ has a solution exactly like that. These are called templates. We can use templates as placeholders for any user-defined classes, as well as primitive classes. Here's how you can use templates in your code. Use the keyword template followed by angled brackets. Then inside the angled brackets, you specify your placeholder name. Traditionally, people just use capital T as the name, but you can use any other name. Then put this line of code in front of the class or function you want to extend. Then you can use T just like a regular data type in your code. The compiler will replace the placeholder T with any concrete data type you specified. And that's exactly why it's called a template. With templates, you can easily make a copy with small changes. Let's now see an example of using templates to extend our stack class. The left side is the stack class we created previously. Pay attention to the integer data type in red. These are the data types of the elements in the stack. Those are what we want to replace with a template. The right side is the same class extended with templates. As you can see, it simply replaced the data type of the elements with the placeholder T. Let's talk about the implementation of member functions. First, since the class is now a template class, instead of just using the class name to specify the namespace of each member function, we can use the class name with the placeholder T in angled brackets. Let's start from the push function. We know the variable count keeps track of the number of elements in the stack, and the variable size is the capacity of the stack. So we first check whether if the stack is full or not. If not full, then the new item will be assigned as the next empty position in the array. That position has the index equal to count. After this assignment, the variable count increases by 1. This is done by the two plus signs after count. Then let's look at the pop function. We can pop only if the stack is not empty, so we check whether count is larger than 0. Then we decrease the count by 1, and that's the index of the element at the top of the stack. This function will return that element. Please note the two minus signs in front of count. That means the count is decreased before we use its value as an index. In both the push and pop functions, the stack is modified. So does the count value. The size function simply returns the count value. The top function returns the element at the top of the stack. That means the element at the index of count minus 1. Please note the count value doesn't change here, because we know the top function does not modify the stack. Through this code, if the operation cannot be done, we simply throw an exception. Now, the stack class implemented using templates, how do we use them? Here are some examples to use the template class to create copies for different data types. We can call them template instantiations. In these examples, we instantiated 3 copies of the stack class with int, double, and a custom class as the data type. Each stack object then acts as the stack data structure for that specific data type. Another similar data structure is called a queue. Unlike stacks, queues implement FIFO, or first in, first out. Like stacks, queues can also be illustrated by real-world scenarios. People leave the queue from the front and enter the queue at the back. The queue also has two main functions, NQ and DQ, where NQ is to add a new item to the back and DQ is to remove an item from the front. We also have a couple of additional functions. Front and back will return the element at the front or back. Size will return the number of elements inside the queue. Now let's see how to implement a queue with an array. We're going to implement the NQ first. First, we need a head index and a tail index. The head index will handle the DQ function, while the tail index will be used for the NQ function. Let's assume we already have a queue within an array. The head index will keep track of the front element of this queue. The tail index keeps the next empty position, following the last element of the queue. If we add a new item 10 to the end of the queue, it will take the position where the tail index is pointing to. Then the tail index will move one step to the right. Now here's the tricky part. What if the tail index is already pointing to the last position in this array? In this case, it will wrap around and start from the first position if that position is empty. This wraparound can be implemented using the modulus operator. We will see that in the code shortly. DQ is implemented similarly. Instead of updating the tail index, we update the head index. Let's assume we have a queue in this state, where the tail already wrapped around, so this queue is 4, 5, 1, 2. In that order, and 4 is the front element where the head index is pointing to. Now we call DQ once. It will remove the number 4 and move the head index one step to the right. Like the NQ trick, if the head index is already pointing to the end of the array, then it will wrap around and start from the beginning again. Now let's look at the implementation of a queue. First, we define the class. There are two additional variables compared with the stat class. The head and tail indices. Both are initialized as 0. This is the NQ function. First, we assign the new item at the tail position. Then we increase the tail by 1. We use the modulus operation to wrap it around if it reaches the end of the array. At the end, we increase the count by 1. Now let's look at the DQ function. The front element is what the head index is pointing to. Let's save a copy to item. Then we will move the head index one step to the right, and we use the modulus operator to wrap around it. We will return the item after the count is decreased by 1. You may have noticed the function doesn't actually remove the front element from the array. The element is still in the array, but the head index is updated. That's enough since the head and the tail indices specify the queue inside the array. I'll skip the other functions since those are self-explanatory. The queue class can also be extended to a template class, but I won't repeat that here. In summary, we learned about stacks, which implement LIFO, and queues, which implement FIFO. Their implementations don't include any loops, so we know all the functions run in constant time, or O(1) time. In this lecture, we use arrays to implement both stacks and queues, but they have other implementations, which we'll talk about later. We also learned about C++ templates and how to use them to extend existing classes. This concludes today's lecture. Have fun and happy coding. I'll see you next time. Bye bye.